Hello guys and gals, my name is Gyuszi. I'm going to present integrals in 5 minutes or less. Let's say we have a function f of x drawn in red here. I would like to compute the area under the curve drawn with these gray bars, gray rectangles. And I'm trying to find a function g that will help me compute the area. Let's assume that function g exists. It needs to have certain properties to help me compute the area. Namely that if I pick a value x here, and this is x plus dx because the width of these rectangles is dx, the values of function g at those points is the gx plus dx and the g of x, and the difference between these two y values is drawn in yellow. Let's call this a, which is a one-dimensional value, and if that a is the same as the area of this rectangle, highlighted in yellow, then function g is the function that I'm looking for to help me compute the area under the f. So this will be f of x at the green x. So let's assume that function g exists. That represents the area under the curve f of x. So g of x plus dx, which is this y value, minus g of x, and the difference is the a, the yellow line, should be the same as f of x at the green x, which is the height of this rectangle, multiplied by dx, which is the width of the rectangle. And if these two are the same, that means that this two-dimensional value of a is represented with this one-dimensional difference between these two y values of g. And if we pass the dx to the left, we end up with this expression. And as d is becoming smaller and smaller, it's trending towards 0. Then basically we get this, where g is the antiderivative of f, where f is the derivative of g. So let's say now we want to compute the sum of these four rectangles a, b, c, d. They all have the same width dx. And I would like to compute the sum of this area. So a is g at value 2 minus g at value 1. And b is g of 3 and minus g of 2, all the way to the area of d equals g of 5 minus g of 4. So the sum of these four rectangles, sum of a, b, c, d, equals g of 5 minus g of 1. And actually I left out the dx here, so this should be, give me a second, f of x times dx. And this is f of x times dx. Okay, so what it means is that the f of x is the red line multiplied by dx. This is the sum of these gray rectangles equals g of x plus k. K is a constant. So if you compute the derivative of g, we get f. So to compute the area of these four rectangles, we basically say the from 1 to 5, and equals g of 5 minus g of 1. So let's put it in context here. Let's say the function f is cosine of x, and so I'm trying to compute the area under the cosine of x. Notice that here I'm using degrees, 0 through 90 degrees, and this is the cosine. And I'm also using radians here, and this is 1. It's 100%, so this would be 1. And I'm trying to compute the area under the cosine times d of x equals sine of x plus k. So the pink area, which is from 50 to 80 degrees, of cosine of x times d of x equals sine of 80, which is here, minus sine of 50, which is that's the area in pink. So let's look at now both functions drawn. The cosine is here and the sine is here. And you can see that we have, so these vertical lines are drawn at 2 degrees each. And so 1 degree would be 0.017 radians, and 2 degrees, that's how I drew here, 0.035 radians. And if I look at the area of this tiny sliver here, which is 0.021, that's the area of this. And how it is computed, I took the 52 degrees value, which is here, so cosine of 52, multiplied by 2 degrees, which is the width of this rectangle, 0.035, equals 0.021. So that's the area of the first pink sliver. And the area of the last pink sliver is 0.006. So if you take the 80 cosine of 80, which would be the right side of the height of this rectangle, multiplied by 0.035, you will get the value of 0.006. Okay, so we want to compute the area of this pink, area here under the cosine, and that is the same as sine of 80 plus k minus sine of 50 plus k. Well, sine of 80, we are here, is 0.984, and sine of 50 is 0.766, and the difference of the two is 0.218, which happens to be the same as the area under the cosine between those two values. And that's the beauty and elegance of the integral calculus. Without that, we would have to compute this manually, which would be way, way worse. Okay. That's all, folks.